Alright then, today's Hack the Box challenge we're going to be doing today is going to be called Optimistic, which is a Pwn challenge from Hack the Box. So, how to solve this challenge? So, the main point of this challenge was understanding integer overflow. So, what is integer overflow? So, right here, I have an example of an unsigned integer being passed in an integer value. And in our case, I could pass in any integer value onto this unsigned integer. And then right here, I have it printing out as an unsigned integer. Then I have it printing out as an integer, so the unsigned integer gets casted. Casted means being turned into an integer. And also, this is just extra color. This is just me goofing off. But anyway, then this printf is casting the unsigned integer as an unsigned long. So we're about to see what happens if we cast these values. So once we put in -1, we see that unsigned integer, it doesn't get printed out as -1. It gets printed out as this huge number right here. And then integer gets represented as -1. And unsigned long gets represented as this huge ass number as well. So why does this happen for the most part? So in this example, I have signed and unsigned, integers. So with unsigned integers, they seem to be only positive numbers, while signed integers could range from positive to negative. And if you see right here, integer is a signed integer, so -1. If we pass in -1 and it gets casted as a integer, we see that signed it could range from positive to negative, but with unsigned, it can't range. It ranges to this big old number. So why does that happen? So in this case, we're using a smaller number set. You see 0 right here, right? What happens with -1 since it's not part of the range? Because unsigned is only ranges from 0 to 225. So since it can't go to the left side, you know what it does? It wraps around. So 0, the -1 wraps around and it starts again at 225. So most likely the number, if it gets casted as an unsigned in this example, it's most likely going to be 225. And we could see this just by typing up what the max number of unsigned integer is. So if we look up unsigned integer biggest value, it ranges from 0 to 42942. So it ranges from these are the two number it ranges. You see how there's no -1? Since there's no -1, it wraps around all the way to the end or to the biggest value, and it goes to that number. So in our case, it equals to this value. And this value looks very similar, doesn't it? Because if we go back to our slides, you see it's the exact same number. So that's basically what's happening, and that's basically the main one of the main ways to get inside this main ways to start off with this exploit. So if we check this binary, for the most part, you could check for its permissions. I already wrote a Python script to check the permissions. This is the way I do it. You don't have to do it my way, like I've been saying. So I do python 3 check.py. So we see NX is disabled, so that gives us a hint right away that we could write shellcode for the most part. So other than that, we could probably play around with the binary and see what it does. So we just do optimistic. We just get these. I'll just type no right away. So no exits out. So we type yes. We could put in a value. So Danny, and then we get some kind of it looks like address right here. So I'll just type random value right here. Age, I'll type a random value. Then length of the name, I don't know, I'll just type a value, random value, and it says, whoa, there, you shouldn't be too optimistic. So I guess length of the name, it gives us a restriction for the most part. But anyway, no more guessing. We can just look at the binary. So if we jump straight right into the binary, we see that whatever is printed out, and it gets one chart at a time. So we see right here, we put something that's not equal to y, it just exits out right away. So we had to press on y to get past this. So once we enter something greater than y, we see that this printf statement gets called, and we see that printf statement is being passed in RSI, and RSI holds whatever RAX holds, and RX holds to whatever RBP holds. And if we keep going back to this, we see RBP doesn't get called or doesn't get messed with for the most part. But when we look back, we see the last value that gets initialized to RBP is RSP, but that's like right at the beginning. So RSP or RBP or RSP is basically the stack pointer, which points to the top of the stack, and RBP holds that value. And then RBP later on passes it on to, if we go over here, printf. Oh, RBP right here. We see that, we see RBP gets passed to RX, and RX passes it to RSI. And then later on, it gets called inside this. So RBP holds the top of the stack. So what this is holding, what this is printing out is basically the stack pointer, which is the very top of the stack right at the beginning of the code. So then let's get even more started. So once we figured that out, we could probably use that for later. So it says, please provide us your detail. So we read it in our email, which is 8 bytes long, and we get in 8 bytes. Then we read in our age. Our age gets passed to AU stack 70, which is 8 bytes long. So that, and we can only put 8, which is normal. And then finally, we get to the printf part where we scan something. So what are we scanning? So if we click on this, we see on the left side it's percentage %D. It's very similar to what I wrote. And then local 84. So what's local 84? Local 84 is an unsigned integer. So we could pass in we could scanf any type of integer value to this unsigned integer. And if we look right here, we can only put 64. Anything greater than 64, it exits out right away. But if you see right here, it gets casted as or local 84, which is an unsigned integer, gets casted as an int. So if you're starting to if it's starting to click, we could pass in a negative number right here, and since a negative 1, since it gets casted as a negative 1 right, since it gets casted as an integer, and we see that 64 is actually less than negative 1, so this exit never happens for the most part. And now if we go look right here, we see that local 84 is used to read in local 68, and local 68 is a buffer of 96. So that means beforehand we couldn't pass in 64 bytes to this 98 byte buffer, or I'm not sure if bytes the right word, but like, you get what I'm trying to say. And with since now, let's say if we put in negative 1, that means we could put in what's the value of ulong? What was the technically ulong? We could pass in this 98 byte and a large number bigger than 96. So that means this could be a very large. It could be like the biggest number of ulong, which is if we go back right here, we could technically pass in a 96 buffer could pass in I don't know what this number is, like 4 million or 40 million. So which is crazy. So that could lead to a buffer overflow. So I guess how do we piece this together for the most part? What we want to do is get a buffer overflow to control the stack pointer. So basically, for the most part, what we're going to try doing is cat solve.txt. I'll just do backcat because I like the. So we know that NX is enabled, so that means we're able to write shellcode to get a shell. And we know we have an array of 96, and we can insert more values into this because of a buffer overflow or integer overflow because of the negative 1. So what we want to be able to do is write shellcode at this array buffer, and then whatever the size of our shellcode is, we add in whatever is missing until we reach RSP, which is a stack pointer. And then from RSP, we could put the beginning of the array, so it could point back to where our array starts, and it runs our shellcode to get shell. So basically, shellcode plus a bunch of A's plus the address of the shellcode of where it starts of our array. That's basically what we're gonna try to do. So I guess one of the very first things is, how do we reach our RSP, I guess the stack pointer for the most part. So we know that we're able to cause the buffer overflow. So how do we reach that? So we could basically reach we basically know how to reach the buffer overflow just by clicking on local 60 local 68, because this is where the buffer overflow is happening when we're reading this value in. If you click on local 68, we see that local 68 holds OX68. So if we just simply copy this for the most part, OX68 to decimal, it's 104. So 104 is gonna be how we reach are like the RSP. So basically what I have here is solve.txt. So basically the shell code and plus the random value has to equal to 104, and then the shell code plus the random value, then we have to put in our address next of our array. Now how do we figure out the address of our array? So basically, since the stack pointer is revealed to us right at the beginning or right at the start, where it says right here printf great. Okay, right here, since it gets printed out right here, we see RBP holds the last value of the stack pointer, and the stack pointer is right here. And we see that all these values get pushed into the stack, and we want to be able to reach 96. And if you guys don't know how the stack works, basically you can think of it how you're stacking books. So this is the first book that gets stacked, so that's one book on top. Then we got another book being stacked, and a third book, a fourth book, and the last book being stacked. So the book that's on top is char local 68, which is starts at 96, which is 96 bytes. And we know that RSP is a stack pointer, so it points to the top of the stack. So you could think of it like this. So like nano stack dot txt. So we have let's do stack 78, stack 70, and then local 68, and then the RSP, which is a stack pointer, is right here, and which is what's being leaked out from the stack. So RSP holds and points to the top of the stack, which is the end of 96. So how do we figure out RSP since that's being leaked out? Let's say a random address of OX, and then we just put a random address. That's basically the top, but it's pointing at the end of it, basically. What we technically do to reach the beginning of local 68 is just simply subtracting 96. So all we need to do is just do OX plus whatever it prints out, the random address, minus 96. And that's how we reach the beginning of our array. So that's basically it for the most part. And then I guess I'll show you my code for the most part. So if we go to nano solve.py or nano solve.py, we see right here that I have ELF, the optimistic binary LE-ELF process send line. Would you like to enroll to yourself? We put yes because we want to be able to reach the other values. Great, here's a small gift. So right here with the stack leak, since we receive line and we decode it and we turn it to an integer value, right here, the stack leak, and then right here we print out the stack leak. So right now the stack leak is stored inside here, and then I'll explain the shellcode later on. So anyway, we send in like just arbitrary values. This could be whatever we want for the most part. I'll even change it right now. I'll even change it to like a bunch of C's or something, so you guys can see. This could be anything for the most part. Anyway, from right here, we start off with our shellcode, which I'll explain what this shellcode is for the most part. So we start off with our shellcode, and then after that, we add in A's depending from the offset, and the offset is basically 104. And like I said before, we got this 104 value from looking at Gija right here. Local 68. OX68, and OX68 is 104. So we go from 104 minus the length of our payload because we want to see what how big our payload is, and then we just want to fill up the rest of our payload with A. And then we have the stack leak, which is the top of the stack, like right at the beginning when the code gets executed. And we see that we subtracted by 96 so we're trying to reach at the beginning of the array to point at the beginning. So once that gets into play right here, basically what's going to happen is that the instruction pointer is going to point at the stack leak, which is going to point at the beginning. And it's going to run this part of the shell code, and then it's going to give a shell. And I guess what you're asking is why this value? Like, why this shell code for the most part? Why is it like all alphabet numbers or alphabet or numbers? The reason being is because the reason being on why we're restricted like this is because this is alpha. This is alpha is checking our, I guess, whatever's inside this array into our local 60. So it's checking in our local 60 if it's an alpha or not. So I guess another part is like how do we write shellcode that is alphanumeric? That's very easy actually. Like you could just probably search this up, shellcode alphanumeric. So it's checking for shellcode that's alphanumeric. So alphanumeric shellcode. And the way I found it, for the most part, I was reading a write up, and supposedly they found it at a specific site. But let's see if I can just copy and paste. I'm pretty sure this is a generic shellcode. So if I just copy and paste this, and just go right here, and just Google Dorkit. Yeah, right here. This is gonna give us a exe bin sh shell. And you can just copy it from right here, and it tells us how they built it right here, which is pretty crazy for the most part. You could probably read more onto this to see how it's built, but this is basically how it's built for the most part. So, because what I tried doing is using Pwn Tools is a alphanumeric feature, but it didn't work for the most part. So if I tried doing this using hello, oh yeah, if I tried running this Python 3 solve.py, if we get end of file error, and my bad, my mic disconnected for the most part. I need to get a new mic. Anyway, we get end of file, but if we go back right here and just copy that shell code that I found from exploit DB, we see that it's gonna work. So if we try this, for the most part, Python 3 solve.py. So if we try this, we get a shell. So now what we want to do is be able to check ls and see, look, we see all of our flags, or we get a shell to our machine. Now what we want to do now is be able to, since it works locally, we want to be able to test it out remotely. So what I'll do is just copy this value, do nanosolve.py, and just change this process to p equals remote, I think, and then we just do something like this for the most part. So we just copy this, and then we just put that value in, and then we just paste it right here. And then if we just write this, we should get a shell now. Python 3 solve.py, and then boom, we get a shell. So we type ls, we see the flags, and we just do who am I, and we see we are root, and then pwd home ctf. Yeah, see, look. Now if we just write cat.flag.txt, we get the flag for the most part. So my partner needs to sign in, damn it. Oh, I accepted it. Ooh, let's go. So anyway, yeah, that was about it for this challenge. For the most part, it was mostly, I guess, understanding a bit of understanding how the stack worked for the most part, and also understanding about the is alpha thing. The it's checking our array of local 68 to check if it's alphanumeric. So I guess that was like a bummer for the most part, but we found shellcode that works for alphanumeric stuff. So that's one thing I learned about alphanumeric shellcode, and the integer overflow, buffer overflow without like to reach, I guess I guess to reach the buffer, and then I guess also how I just leaked the stack pointer, the like right at the beginning, and basically this whole thing is a stack when it gets initialized. This gets put on top. This is like at the very bottom. So to reach this var91, you probably need to. Do they have it right here? They don't have it, but what they do have is what's the lowest thing on the stack here? Local 88. Yeah, OX 88. So local 88 is it right here? It's not right here. Probably gets initialized later on, but that's probably like the lowest part of the stack. Or there's probably more parts, but anyway, yeah, I guess understanding how the stack works for the most part, and then just the is alpha numeric code and just the integer overflow for the most part. Anyway, that's about it for this challenge. I've been talking a lot. Hope you guys learned something new today, and yeah, that's all. Peace.